Hello everyone, welcome. Um, in the last set of videos, we introduced vector functions and parameterized curves. In today, we are going to start the next set of videos on vector functions. Uh, Particularly, we will be talking about limits of vector functions, derivatives and integrals of vector functions. Let's recall that a vector function is a function the where the domain is a subset of the real numbers and the range is a set of points in R3 or R2. And in fact, we can even talk about vector functions in the n space for any n. So that is, when you have a vector function, the input is a real number and the output is a point in the space, or it is a position vector in the space. Now, if we have a curve C, if we have a curve C that is parameterized by this vector function R, what we mean is that each point on the curve is the value of this function R at some input t. Now I'm putting an arrow on top of R to signify that it is a vector function, but most of the times I don't put that arrow. I'll be a bit sloppy with the notation, but the context should be clear. So what do we mean by the limit of the vector function R of t as t approaches the real number a? Well, what it means is that the length. So this is the length of the length. So here L is a vector. So the limit of R of t as t approaches a is the vector L. Means that the length of R of t minus L can be made less than any desired positive number epsilon by choosing any t in some suitable open interval centered at A. So that is so what it means is that as t approaches A, the vector R of t, or the point R of t, is approaching the vector L, or the point L. So if R of t has components x of t, y of t, and z of t, then it turns out that the limit of R of t as t approaches A is the same as the following vector, where is the same as the vector where the first component is the limit of x of t as t approaches A, second component is the limit of y of t as t approaches A, and the third component is the limit of z of t as t approaches A. So in other words, when you're taking the limit of a vector function, you can just take the limits of the components of the vector function. So here's an example. Let's say R of t is the vector function where the first component is 1 plus 2t cubed, the second component is t squared e to the negative 3t, and the third component is sine t. And so if I want to take the limit of R of t as t goes to 0, what I'm going to do is I'm going to take the limit of each component. So I take the limit of 1 plus 2t cubed as t goes to 0, and then I'm going to take the limit of the second component. I see that I forgot to write limit in these two terms. So let's do that. So here I want to write the limit as t goes to 0 of t squared e to the negative 3t multiplied by j plus the limit t goes to 0 of sine t okay. So now of course the limit here is obviously 1 as t goes to 0. The limit here, if you recall from what you did in calculus 1 or 2, where you went over the L'Hopital's rule, if you use L'Hopital's rule here, you can write this as t squared divided by e to the 3t, and the limit of that would be 0 as sorry, you don't have to use the L'Hopital's rule, because as t goes to 0, e to the negative 3t goes to 1 and t squared goes to 0, so then this limit would be 0. So no need for you can't apply L'Hopital's rule, and no need for that. And then the limit of sine t here would be 0, of course, as t goes to 0. So then I get that the limit of r of t as t goes to 0 is the vector I, which is the vector with components 1, 0, 0. Okay, so the point is we can take the limit of a vector function component wise. That is, when we take the limit, we just take the limits of the components of the vector function. Now we say that a vector function r is continuous at a if the limit of r of t as t goes to a is equal to r of a. Okay, so with that I'm going to stop this video. In the next video we will be looking at the derivative of a vector function.